All right, hello everyone. In this video, I'm going to validate the results of the model or the compositional two-phase reservoir simulator that we developed in the previous video by comparing the results of that with the results of Open DARTS. So as you already know, Open DARTS, which stands for Delft Advanced Research Terra Simulator, is the reservoir simulator of TU Delft, and you can install it by executing this command pip install opendarts, and um, you need to execute it in your terminal. And I will talk about this and how to install it in detail in the next videos. So um, let's start, talking and validating the simulator that we had in the previous video. This is what we had and what I talked about. These are uh, three different folders that I talked about. And the properties of the models that we have in all of these three folders are the same. So just choose one of them. For example, choose this one, this folder, and open the main module, the main script. And so I'm going to compare the results of this with the results of the script that I have um, created using OpenDarts. And I'm going to simulate the same scenario that we have here, uh, which we used our own simulator to simulate it with the results of OpenDarts. So as you see here, I have imported and I have used some of the modules in the package of OpenDarts. So you need to install it first. And this is the script that we have, and we need to run it. Let me briefly talk about it. So we start from here. First of all, we had a few functions which are called from here. So the first line here is the function activate timer. Using this function we actually activate some timers, and what it does is that it calculates the runtime of different parts of the code. So let's get into this function. So as you see, it calculates the simulation time, the initialization time, and things like that. So this is actually what this function does, which is the calculation of the runtime of different parts of the code. The second line calls the function define params. Using this function, we specify the first time step size, the time step size multiplier. So the first time step size is this, 0.01 days. The second time step size is 0.04 days because the multiplier is 4, and so on. The third time step size will be 0.16 days. All right. So the maximum time step size is 1 day, and the tolerance of the Newton-Raphson solver is set to this value. So in this function, we specify such parameters. Let's get to the next line of the code. Here we specify the number of cells of the reservoir. If you look at the main script that we had in our own simulator, here we also had 10 cells. We have a one-dimensional domain with 10 cells. So we also have 10 cells as well, because we're going to create the same model and compare the results of that with the results of OpenDarts. Here we initialize the mesh. Number of cells is an input argument here. Here we actually create some vectors which are used for the connection list. Here we evaluate the transmissibility. Permeability is 1 millidarcy, and the transmissibility is equal to Darcy coefficient. Darcy coefficient, transmissibility is equal to Darcy coefficient times permeability times cross-sectional area, 5 times 5 cross-sectional area, as you can remember from this main script that we have in our own simulator. So our cross-sectional area, which is perpendicular to the direction of the flow, is 5 times 5, and length, the distance between the centroids of the neighboring cells, is also 5 meters. All right. We have the length of the model is 50 meters, and the total number of cells 10. So each cell is 5 meters, and the distance between the centroids of neighboring cells is also 5 meters, and that's why we have written 5 as the denominator of this fraction. All right, so here we evaluated the value of transmissibility, and transmissibility is evaluated only at connections, and because of that, when we have a one-dimensional domain, so let me create a one-dimensional domain, and I have a number of actually I have a number of cells. All right, so I have a number of cells, and so for example, in this case, I have 1, 2, 3, 4, 5, 6, 7. I have 7 cells. The number of connections is 6. 1, 2, 3, 4, 5, 6. So that's why the number of values that I have for transmissibility is 1 less than the number of cells. All right. So after that, inside this function, after evaluating the transmissibility, we initialize the mesh in this way. This is for connection list. This is transmissibility, and this is actually for diffusion. And this is another function that does something else, and you don't need to know about it. You don't need to know what it does for now. And it returns this object, which is a C++ object. It's a C++ object because, as you probably already know, DARTS works with C++ as well. So actually, it uses both C++ and Python for simulations. And that's why in this case, for example, we have mesh as a C++ object. So now that we are done with mesh, we define some other parameters here. Here we specify the bulk volume of the cells. These are actually, as I said, mesh is actually a C++ object. So we create NumPy arrays wrapped around mesh data. So we create NumPy arrays, and as we change the values of these variables, the values of these variables in C++ also change. All right, very good. So here we set the volume of each of the cells to this value. We have 10 cells, so we set the bulk volume of each cell to 125. Why 125? Because the width of the cell is 5 meters, the height is 5 meters, and the length is 5 meters. And so the total bulk volume of the cell is 125 cubic meters. The porosity is 0.2, and then we specify this porosity variable to this value. And we set the depth to 1,000 meters in this case. It doesn't really matter what value you set here. And here we set the boundary volumes. The first grid cell, we set the volume of the first grid cell to a very, very large volume, and also the last grid cell to a very large volume. And actually they behave as the boundaries of the reservoir. All right. So we are done with this function. So let's move on to the next one. Here we specify the initial and boundary conditions. Again, we have mesh, which is a C++ object. We create wrappers, pressure, mole fractions, the initial pressure of the reservoir 200 bar, the injection pressure, I could say, which is the pressure of the first grid cell of the reservoir, which has a very, very large volume, is 250. Or I'd better say that the first grid cell of the reservoir, which has a very, very large volume, the pressure of that is set to 250, and the pressure of the last cell of the reservoir, which has a very large volume, is set to 150. And the initial mole fraction of the reservoir, which is actually the mole fraction of CO2, is 0. 0 is a very small actually value, and this indicates that we could say that we have only water in the reservoir initially. And as the boundary condition, we consider that the first grid cell of the reservoir, which has a very large volume and its pressure is set to 250, is saturated with CO2, 1 minus a very small value. And so as the simulation starts, CO2 in the first cell of the reservoir, which I repeated, I mentioned repeatedly, and it has a very large volume, the CO2 flows from that cell into the reservoir, all right, because it has a higher pressure, and due to that actually pressure difference, the CO2 flows into the reservoir, which contains water. All right, so here we specify the boundary conditions. We also specify the boundary conditions in this function as well, but in this case, we only set the total volume, all right? Or this is actually, I could say, yeah, the total volume. That's correct. That's the total volume, bulk volume. All right, so we also talked about this function, and now we define the physics of the model. We say that we have CO2 and H2O as the components in the system. We have two phases in the system, gas, which is the CO2 rich phase, and the aqueous phase. Here we specify the molecular weights. This is the molecular weight of CO2 This is the molecular weight of H2O. Here we create or instantiate the class property container, and we pass these actually input arguments to this class, the constructor of the class. And after we get an object of this class, we add correlations of the properties. For flash calculations, we use constant K values, and these are the constant K values that we have used, and we actually store this correlation. We store, which is actually a class. As you see, it's a class. We store an object of this class in this variable, and we also create some objects, some other objects to evaluate the density of the gaseous phase and the density of the aqueous phase. As you see, we have used very basic functions to evaluate the densities, which is a function of pressure, and that's why we have specified compressibility here. Compressibility. And this is the correlation that we have. Compressibility times 1 plus, the density of the phase under reference conditions times 1 plus compressibility times the intended pressure minus the reference pressure. And this will give us the density at this intended pressure. So this is actually the density basic, the description of that. This is the compressibility, and this is the density of the phase under reference conditions. The gaseous phase 200 kilograms per cubic meters, aqueous phase 600 kilograms per cubic meters. So for viscosity evaluation, we have actually used constant values. For the gaseous phase 0.05 centipoise, for the aqueous phase 0.5 centipoise. And we have stored them in a dictionary, the same as the previous one, and we store the dictionary in the viscosity evaluator variable, which is a property of this class, the same as the others. Density evaluator, flash evaluator, rel-perm evaluator are all the properties of this class. And now it's an object, right? So after that, we actually use some correlations for relative permeability evaluation. And this is actually Brooks and Corey model that we have used here. And we store it in this property. After that, we activate physics. We instantiate the compositional class. These are the input arguments of this class. These are this is the list of components. This is the list of phases. This is the timer that actually we defined. This is the number of OBL points. This is the minimum pressure for the OBL domain. This is the maximum pressure for the OBL domain or parameter space. This is minimum mole fraction and maximum mole fraction for the OBL domain. And after that, we call this a method, and then we initialize physics in this way, and we return these two variables, physics and engine. Of course, you can use OpenDARTS in many different ways. This is just an example of that that I was going to show you here, and just to validate the results of our simulator. So we returned two variables, physics and engine, we initialize the engine in this way. This is the mesh that we defined, and some other things that we have as input arguments. Here we instantiate the DARTS model class. Here we have an object of that because now the initialization is completed. We stop the timer for the initialization stage. And now it's time to run the simulator. So we use this object of the DARTS model. We use the run simple method of the class of the object to run the simulator. And physics is the first input argument of this function, and params is the second input argument, and 100 is the total simulation time. All right, so we are done, and now it's time to run the code ourselves. So all right, now it's finished, and now we can see, and as you saw, it was very, very fast. We couldn't even see how these lines were generated. So at the end, we plot the profiles, the pressure profile and the CO2 mole fraction profile along the domain. This is the pressure profile after 100 days. This is the CO2 mole fraction profile along the domain. And if we get these values, if we get, for example, let me run the script again and stop the simulator here. This is the pressure profile at the end of the simulation after 100 days. So let me see the values. So these are the values: 249, 150. So if you compare the result of this with the results of, for example, this simulator, for example, main, let me see if I can show you the results of that right here. Okay, the results are stored in these pickle files. The results are stored in these pickle files. Maybe I can use this module to see the final pressure profiles. So let's have a screenshot. Let's have a screenshot of this pressure profile, which was generated by OpenDarts. And now let me make sure that this script is run as well. So, all right, it worked, and the results are stored in these 3 pickle files. So if I run this function, we will have the output. For example, the pressure profile. I think now we have the pressure profile after 100 days. And as you see, if we compare the pressure profile, they're very, very close. 249, very, very close. 150, 150, and it's also the case for the case of mole fractions. So if I'm going to show you also CO2 overall mole fraction, profile after 100 days. So this is CO2 overall mole fraction profile after 100 days. Let's keep this in mind. Let's keep it as a screenshot. And now I think we don't need this script anymore. So let me close all of these scripts. And now let's run this DARTS script again. And what I'm going to see now is the results of mole fraction. All right, so here we have mole fraction of CO2, and let's compare it with the results of our own simulator. All right, 4.8, 4.7, very close. 6.1, 6.1, 2.5. As you see, they're very, very close. 10 to the power of minus 10 or 10 to the power of minus 9. You know, their difference is very, very negligible. They're very, very, very small numbers, both of them. All right, so look at this one, 1.5, 1.49, very close. And you know, those little differences are just because of the, you know, the calculations and, you know, the accuracy of the, you know, calculations that are done in the system. All right, so that's it. That's what I was going to talk about. And you can also, you know, see the results here. I put them in this Excel file. This is actually what we have. These are the results that we have from DARTS. These are the results that we have from Flow Simulator Simplified Mole folder. And this is from Simplified Mass. This is Simplified Mole. This is Simplified Mass. And this is Flow Simulator. This is Flow Simulator. And all of them, the results of all of them match. All of them are on each other here. What you see here is the results of another simulation, which I will talk about in the next video. All right, so, and as you see, all of the results are, you know, all the points of these simulators, all of these 4 simulators are actually on each other. All right, but this one is different, is another thing, which is actually this one. This one, the results of this one is different, which is actually because of another reason that I will talk about in the next video. And it's actually because of the upwind scheme. But I don't need to get into that now. I will talk about it probably in the next video. All right, so here I showed you the validation of the simulator that we developed in the previous video. And yeah, that was, I think, all what I was going to talk about. So I hope you're having a great time, and thank you for tuning in.